When students are first introduced to the idea of electric current, it's often described as a flow of electrons down a wire. So here's a wire, here are some electrons, and they are fair booging it down that wire. They're racing down the wire. Unfortunately, that's not quite how it is. Are the electrons moving really, really fast? You betcha. We're talking millions of kilometers per hour. So yes, electrons do move really, really quickly. But is that how fast they're moving down the wire? No, actually it isn't. Electrons are moving fast. Let's just draw very quickly the structure of a piece of metal. These little circles here represent electrons. What am I saying? No, they don't. They represent atoms. So there are these atoms in the metal. Now, the outer electrons, outer shell electrons, are called the valence electrons. The valence electrons for metal atoms don't stay with their atom that they're from. So let's say this atom at the top left corner has an electron. Here it is. That electron isn't just going around and around and around the nucleus. Okay, with a metal, what happens is that those valence electrons are actually free to move anywhere at once throughout the entire metal structure. So it doesn't stay with, its atom. Here's another electron, let's say from this atom here. It doesn't stay at that atom. It's randomly moving throughout the entire metal. We describe the metal's electrons as being delocalized. The valence electrons aren't localized around their own atom. Okay, so the valence electrons, the outer shell electrons, are moving all over the place throughout the metal bar, and that's what is happening really, really quickly, millions of kilometers per hour. But when we hook up our piece of metal, let's just get a wire sticking out here and a wire sticking out here, and at the other end, maybe we have a battery. So we hook it up, and now we have a flow of charges. Actually, that's another thing I should point out. Electric current is often described as that flow of electrons. Well, actually, a flow of charges would be a better way to describe electric current. Often, the charges are the electrons moving down the wire, but technically, electric current isn't a flow of electrons, it's a flow of charges. Now, that flow isn't actually fast. Sure, in our metal bar, what is this electron doing? It is whizzing around really, really fast, millions of kilometers per hour. However, it is not racing down through the metal. Let's take a look. We have a certain equation here. We have I equals NAVQ. Right, now, what are all these things? Well, I is the current. Let's just write that in. I is the current. Now, current is measured in amps. So in amperes or amps, we can say. N is the number of electrons. So N, number of electrons. A is the cross-sectional area of the piece of metal. So essentially of the wire that the electrons are apparently racing down, and we'll see they're not racing down at all, but that's the cross-sectional area. V is the velocity. So this is actually how quickly the electrons are moving, and what we're going to do is calculate the velocity and see that it's actually really, really small. Q is the charge on an electron. So charge on an electron. Q is actually 1.6. Let's just change color. This is actually 1.6 by 10 to the minus 19 coulombs. Let's just put it C for coulombs. That's what charge is measured in. Now back to that current, that's measured in amperes, but 1 amp is actually 1 coulomb of charges per second. All right, so that's an ampere is actually coulomb per second. So you can think of current as being coulombs per second there. Now, cross-sectional area, well, that's going to be in meters squared. Number of electrons, well, that's just a number, yes, but it's actually number of electrons in the material. So we've got a three-dimensional material, so it's actually number of electrons per meter cubed. Now this, when we rearrange this equation, this will give us our velocity in meters per second, which a good little velocity should be in. So let's just check that. Let's rearrange this equation. All right, so we started with I equals MAVQ. We want to rearrange to find V, the velocity that the electrons are actually traveling in. Well, we don't want this N and this A and this Q with the V. They have all been multiplied. We don't want them there, so let's just dump them over the other side with the I. So here's the I. But when we take something across the equals, we have to do the opposite. Because with the V they were multiplied by the V, when they're on the opposite side they're going to be divided by. So we have divided by N, and a divided by A, and a divided by Q. So this now is our rearranged equation. This is what we're going to use to determine the velocity of the electrons. And as I've alluded to, it is not going to be great. In terms of doing physics calculation problems, we should start with an equation. We did. There is one. And then you rearrange the equation if you need to, which we did. There it is. And then we put in the numbers. And then we're going to reach for our calculator and get the answer. So let's put in the numbers. Let's say V is equal to, right, so we need current on top, right? We started with I. A good current to use is 10. Let's call it 10 amps. Now I just say this because 10 amps is the general current supplied to Australian households. Okay, if you had like something like a phone fast charger for your phone, that's about 3 amps. But your standard plug, your plug on the toaster, that's generally a 10 amp plug. So there we go, 10 amps, that's the current that we'll use. Now, this is divided by number of electrons. Well, we need to have a number. Let's talk about copper wire because that would make sense. Often when we're doing electric circuits, our wires are copper. It's a very good conductor of electricity, and it's fairly cheap, compared to something like gold, which actually does conduct electricity better, but it's more expensive. So we'll use copper. 8.5 by 10 to the 28. Oh, wait, that's not a 10. That's a 10 to the 28. That's the number of electrons per meter cubed in copper. Okay, cool. So the next thing we need is a cross-sectional area. Well, what are we going to do that? Let's say we use 19 gauge wire. Okay, so in terms of our area, the wire is round, so our area is going to be pi r squared. In terms of r, well, we need to know how thick the wire is. Wires come in all sorts of different thicknesses. We call them gauge. Now, a standard wire gauge 19 is about 1 millimeter thick. Okay, so standard wire gauge 19, it's actually slightly over, it's like 1.016 millimeters off the top of my head, but let's just call it 1 millimeter. It's very close to that, which means that our R is actually going to be only half of a millimeter, right? Because it's the radius, not the diameter. Now, we want to work in meters. Okay, now we should probably, at some stage, let's do it now, point out the units. Okay, so we have V, we had on the top line current, but remember current is amps, but we can think of an amp as a coulomb per second. What did we have on the bottom line? Well, we have the number of electrons per meter cubed, so that's per meter cubed. We had area, which is in meters squared, and we have the charge, which is in coulombs. Now, when we do this, we're going to come out with a nice little unit for velocity, because this, actually, let's change color. This meters squared is going to cancel out 2 of the m's down here. It's going to cancel out 2 of those, and that's going to leave us with just the m, or the 1 over m. Here's a top line c, and look, we're divided by c. They are going to cancel out. You gone, you're gone. So the c's not there anymore. We've divided by 1 over m, which is the same as just m up on the top line. So we're not dividing by 1 over m now, we've just got m over up on the top line. And look, there we go, meters per second. That's the units for speed. Great, that's what we want, meters per second. So back to our equation here. Actually, we can't go back to that. We need to work out the area, don't we? So the area is equal to pi r squared. Now pi, let's just take it as 3.14. The r, remember, is half a millimeter, but we work in meters, okay? So we can't say half, we need to say 0.0005, and that's squared. Okay, and when we do this calculation, we come out with an area of 7.85 by 10 to the minus 7. This is in meters squared. It's a very small area, but that should make sense because we're looking, at a wire end on, right? The wire is not very thick, and we're looking at the end on, so the circle on the end. So yeah, it should be small, and it is. Let's put that number in. What did I just say? I said 7.85 by 10 to the minus 7. This is all multiplied by the charge on an electron, which we mentioned earlier was 1.6 by 10 to the minus 19. So there we go. There's our equation. We're following our steps. Remember, we start with an equation, we rearrange the equation, which we needed to do in this case, then we put the numbers in, which we have just done, we put the numbers in, and then we get our answer. So we punch all this into the calculator, and we come out with an answer of 0.00094-ish. It's actually 0.00093666804 according to my calculator, but I'm going to round it, so it's 94-ish, and we just worked out before our units are meters per second. That is not a very fast speed, right? 0.0009-ish meters per second. That is about, I'm out of room down the bottom, so let's just draw an arrow up the top. That is approximately equal to 1 millimeter per second. So that's the speed that the electrons are actually moving down the wire. And I hope you all agree with me that 1 millimeter per second is not super fast. Okay, those electrons are not racing down the wire at all. They're actually moving pretty slowly. Are the electrons moving fast? Yes, they are, millions of kilometers per hour. But in our chunk of wire, the electron movement is more like this, moving really, really fast. Now the electron started on the left and it's moving really fast, and eventually the electron will make its way down to the right side of the wire, but you'll notice the actual rate that it's moving to the right isn't all that fast. Electrons moving quickly, yes, but because the movement is pretty random all around, the actual driving force across to the right isn't all that great. And it will eventually make its way to the right of the wire. So we actually refer to the movement of electrons down the wire as electron drift. Okay, an individual random electron, it's moving quickly around the wire, but the flow, remember for current we need a flow of charges, so the actual flow of electrons, as we've just seen with this little rough sketch there, is actually quite slow. Okay, so an individual electron moving super quickly, yes, but not moving down the wire super quickly. It's more of a random movement throughout the entire wire structure. But the flow of charges, if we go right back to the start, remember current is a flow of charges, often called a flow of electrons. That actual flow, the net movement of the electrons as a whole down the wire, really, really slow. So yeah, there we go. They're not racing down the wire. We refer to it as electron drift because they're actually moving, in the example that we had, at about 1 millimeter every second down the wire.
Don't forget to hit the like button. Yeah, and subscribe too. It's up here. And here's another video.